SwayamPrabha. Digital India. Educated India.
So if you recall in yesterday's class, we looked at the effect of system poles, right, on the system response. We looked at the fact that the location of the poles essentially influences the stability of the system. So we observed that the location of the poles affected the stability of the system, and for Bibo stability we learned that all our poles of the transfer function, system transfer function, should lie in the left of complex plane, right? So that is, in other words, they should have negative real parts. Okay, so that's the concept that we learned yesterday. So today, I'm going to do a few more examples to convey the impact of zeros, right, on the system response. Okay, so if you recall, the definition of the transfer function, it's the ratio of the Laplace of the output to the Laplace of the input with all initial conditions being 0, right? And we observe that the transfer function is going to be a ratio of two polynomials, n of s and d of s. The roots of n of s are what are called zeros of the transfer function. The roots of d of s are called poles of the transfer function, right? So we have seen that poles are connected to system stability, all right? Now let's look at zeros, okay? So that's what we are going to do today's class. So let's consider these two systems, the first planned transfer function is 1 by s plus 1 times s plus 10. The second system is s plus 2 divided by s plus 1 times s plus 10, right? So what is the order of these two systems? So what do I mean by order? If you recall the general governing ordinary differential equation of the class of systems that we are considering, you have a naught dny dtn, right, on the left hand side. That small n is the order of the system, right? So, and that small n happens to be the order of the denominator polynomial of the transfer function, okay? So if you look at the transfer function, the order of the denominator polynomial is always going to be the order of the system for the class of systems that we are studying, right? So what is the order of the system? 2, right? So n is going to be 2 here. That's the order of the denominator polynomial. What is m? It is 0, okay? So I want you to find the unit step response. So unit step response means u of s is going to be equal to 1 by s, right?
So looking at the transfer function, how can you decide the equation, order of the equation? Maybe it is a third degree equation or m is 1 degree. So how can you decide?
Because you look at the numerator polynomial and the denominator polynomial. The denominator polynomial is a second order polynomial here, right? So of course we are not considering what are called pole zero cancellations, okay? We'll come to that shortly. We are assuming that a pole and a zero are not at the same location, okay? So with that assumption, we can see that the denominator polynomial is of order 2. So we are going to have n to be 2, okay? So if you recall what we did sometime last week, let me go back, I think we wrote down the let me try to see whether it's here. So if you recall, you look at this equation, right? So a naught dny dtn plus a n dn minus 1 yt dtn minus 1. That is the general governing ordinary differential equation for the class of systems that we are considering in this course, right? So if you take the Laplace transform and substitute zero initial conditions, you can immediately observe that the denominator polynomial is going to be a nth order polynomial, right? And the numerator polynomial is an mth order polynomial. So assuming that none of the factors, right, are common between the numerator and the denominator, we could essentially look at the planned transfer function itself and interpret the order of the system, okay? So that's how we write down the values of n and m, okay? So let's say if I want to figure out the unit step response, so U of s is 1 by s. So what happens to Y of s? It becomes P of s times U of s. So I get it as 1 divided by s times s plus 1 times s plus 10. So this is going to be A by s plus B by s plus 1 plus C divided by s plus 10. Okay? Right? Now, how do we find A, B and C? What do you think are the values of A, B and C? We have already discussed this, right? So for A, you just multiply both sides by s, substitute s equals 0, right? So you will immediately see that A is going to be 1 by 10, right? What about B? Minus 1 divided by 9, right? And what about is it minus 1 by 90 or plus 1 by 90? See, you are going to get, you multiply both sides by s plus 10 and substitute s equals minus 10, you will get minus 10 times minus 9. So that becomes plus 90, right? So you will get plus 1 by 90 times s plus 10, right? So with this, if you take the inverse Laplace transform, we are going to get 1 by 10 minus 1 by 9 e power minus t plus 1 by 90 e power minus 10t. Of course, here if you look at the poles are minus 1 and minus 10. Zeros, there are none, right? As far as this particular transfer function is concerned. So this is the output function, right, for this particular system. Is it clear? So that's the output function, right? So once again we can observe that of course the two poles are in the left of complex plane. So the system is bivostable as per our discussion yesterday. So you can see that as t tends to infinity, what happens to the output value? It goes to 1 by 10, right? So the output remains bounded for all time, which you can convince yourself, right? And you can observe that the output function has exponential terms, which is also something which we have discussed. And what are the exponents of the exponential terms? Poles, right? So minus 1 and minus 10 are the two exponents. Okay, so you could observe that all our general discussions are reflected here. Okay, so let's do the same process for this problem. Okay, so once again n is 2, m is 0. The poles are at sorry, m is 1, thank you. Yeah, m is 1, right? So the poles are at minus 1 and minus 10. There is 1 0 at minus 2, right? That's the only difference between these two systems, right? So the difference between problem 1 and problem 2 is that like we have introduced a 0 at minus 2. Okay, let's calculate the unit step response, right? U of s is equal to 1 by s. So this implies that y of s is equal to p of s times u of s, which is going to be equal to s plus 2 times s plus 1 times s plus 10. Okay, so once again we are going to have a by s plus b by s plus 1 plus c divided by s plus 10. So what are the values of a, b and c now? S plus 2 is a factor in the numerator, right? So anyway the order is lower than that of the denominator. Okay, when you take the partial fraction expansion, you only take in terms of the denominator factors. Okay, so you see that there are three first order terms in the denominator. So the residues will be just constants. Okay, the corresponding residues will just be constants in the numerator. Okay, so of course the residues will be different. That's what we are going to come to. Okay, the s plus 2 term, say previously the numerator was 1, now it's s plus 2. So obviously the values of a, b, c will be different.
What if it was square plus 2?
Which one?
Numerator was square.
Doesn't matter, right? So because as long as you are not going to have a quadratic polynomial in the denominator, you can still go ahead. Yeah. Okay, you will still have the same, what to say, a partial fraction expansion structure. Okay, yeah. So what about a?
1 by 5.
Yeah, 1 by 5, right? Okay, b? Substitute s equals minus 1. So what are we going to have? we will have 1 in the numerator, right, and then we will have minus 1 plus 9, right. So minus 1 by 9, it will be the same, right. So I will have minus 1 by 9 times s plus 1, and then like what about c minus, let me write it as minus 8 by 90, okay, for a specific reason, okay. So 4 by 45 I am just writing as 8 by 90, right. So we are going to have minus 10, minus 9, 90, and then like we are going to have minus 18 there, oops, okay, numerator. So I can write it as minus 8 by 90, okay. So this is what we have. So this implies that y of t is going to be equal to 1 by 5 minus 1 by 9 e power minus t minus 8 by 9t e power minus 10t. Okay, that's going to be the solution in this particular case. Okay, fine. Now what do we observe, right? Even in this solution, you can see that as t tends to infinity, the value goes to 1 by 5, right? So it's bounded. Okay, no issues. The system is bifostable because the poles are the same, and you can see that the exponential terms have minus 1 and minus 10 as the exponent. Okay, no issues. But what has changed? So first of all, the steady state value has changed, right? So what was 1 by 10 became 1 by 5 now. Okay, that's one effect. So and then the coefficients of the e power minus t term and the e power minus 10t term have changed. Okay, that's also another impact, okay, due to the 0. And then let's see what is a relative impact due to this. Okay, so let me draw the S-plane, and then we will see what is the impact, right? So in the S-plane, of course, the poles are at minus 1 and minus 10 for both systems, but in this case, we have a 0 at minus 2, right? So in this case, drawing in blue color, right? We have the same two poles at minus 1 and minus 10. That's it, right? So no zeros there, okay? So which pole is closer to the imaginary axis amongst minus 1 and minus 10? Minus 1, right? And if you look at the first response in problem number 1, which do you think will dominate the output term for a longer time, e power minus t or e power minus 10t? E power minus t. Okay, see, we know that as the exponent becomes more negative, the exponential function is going to decay to 0 much faster. Is it not? Okay, so if you consider the magnitude of, the first term, 1 by 9 e power minus t versus 1 by 9t e power minus 10t, what can you say? First of all, e power minus t is going to dominate for a longer time, okay, or affect the output term for a longer time. Yes, of course, as t tends to infinity, both terms will go to 0, okay, both exponential terms will decay to 0. That's a different matter. But then e power minus t will have a longer effect, right, on the output than e power minus 10t. Okay, that's point number 1. Second point is, look at the residues multiplying the two exponential terms, right? So what are they? What factor multiplies e power minus t? 1 by 9. Okay, and what factor multiplies e power minus 10t? 1 by 90. So not only does e power minus t dominate e power minus 10t, the residues are such that 1 by 9 e power minus t will certainly dominate 1 by 90 e power minus 10t to a much larger extent, right, compared to this example. Okay, the next example we are going to come. Okay, so if I want to draw it pictorially, like if we want to draw these two factors, right? So at time t equals 0, anyway e power 0 is 1, right? So e power minus 1 by 9 e power minus t will start at 1 by 9, right? Let's say that's 1 by 9, right? 1 by 90 e power minus 10t is going to start at 1 by 90, right? So 1 by 90, 1 by 90 is 1/10 of 1 by 9. Correct? Let's say it's somewhere there. Okay? So let's say 1 by 9 e power minus t goes to 0, let's say like this. Okay? What will happen to 1 by 90 e power minus 10t? This will go to 0 almost relatively more instantaneously, right? I am just drawing a relative diagram. Oops. Okay, so this will go to 0 almost quickly, very quickly, right? So you see that which factor is dominating the output? 1 by 9 e power minus t, right? So for that reason, the poles that are closer to the imaginary axis or the closest to the imaginary axis are what are called dominant poles. Okay, so -1 here is what is called as a dominant pole. Okay, so dominant pole or dominant poles are those poles that are closer to the imaginary axis. And why are they called dominant? Because you can observe that those poles are going to come as the exponents of the exponential function, and they are going to have a more lingering effect on y of t than those which are farther away into the left, right, off plane. Okay, so that's why they are called dominant poles. Okay, so please remember this discussion. Is it clear what we discussed?
If the coefficient of e to the power minus 10t is sufficiently large, then it will have a sufficient impact.
We are coming there. Okay, so yes. Okay, so is this discussion clear? Okay, we are coming to that point, right? Now, yeah. Yeah, we are only looking at the magnitude. Okay, we are only looking at the magnitude. Okay, let's not consider the sign. I am only comparing the magnitude of the two terms. Okay, yes. Yeah, yes, you are right. I am not considering the sign. Okay, I am just taking the absolute value just to compare the magnitudes. Okay, yeah. Fine. Let's now come to this example, right? So what happened here? We introduced a 0 which is closer to -1, right? So I'm sure all of us agree that -2 is closer to the pole at -1 than the pole at -10, right? Okay. Now we see that once I introduce a 0 at -2, what is the effect of that 0? Yes, it affects the residues. Okay, it affects the steady state values. But if I do a similar magnitude analysis, 1 by 9 e power minus t versus 8 by 90 e power minus 10t. So if you compare those two terms, what can you observe? What can you conclude? See, 1 by 9, let's say we start from here and then we come like this, and then let's say we go to 0, right? So let's say this is 1 by 9. Where will 8 by 90 start? See, essentially if you look at 1 by 9, I can write as 10 by 90. Okay, so 8 by 90 is going to be slightly below, slightly below 1 by 9. Yes, e power minus 10t is going to go faster to 0, but then you can see that now the dominance of the -1 pole is reduced relatively. I'm sure all of us agree to that point, right? So you look at the second case where we introduced a 0 at -2. The consequence of the introduction of the 0 at -2, which is closer to -1, is that the dominance of the pole at -1 is reduced. Okay. Now, so what happens is the following. So as you keep on moving the 0 closer and closer to -1, the effect is going to be reversed. Okay. So what you raised. Okay. Like when will can the residue be higher? Right. As you keep on going closer and closer to -1, what will happen is that the dominance of the pole at -1 will keep on reducing further and further. Okay, I leave it to you as homework. Okay, homework. Okay, try the step response of these two plans, okay, s plus 1.5 times s plus 1 times s plus 10, okay, and s plus 1.1, s plus 1 and s plus 10, okay, and observe. Please do. So what I am doing, like I am just moving the 0 closer and closer to minus 1, okay, correct. So you can see that the 0, the effect of a 0 is that it is going to affect the dynamic response of the system. It is not going to have an what to say, direct impact on the stability, because stability is dependent on the location of the poles. But what do zeros do? You know, like from these two examples, you can observe that the zeros are going to affect the residues, right? So of the partial fraction expansion. So in physical terms, they will affect the coefficients of the response function, right? So if you calculate y of t, the step response function, right? So whatever are the coefficients that are going to come in that response functions are going to be affected by the zeros, okay? And if you have a 0 closer to a pole that is dominant, the dominance of that pole is going to be relatively reduced, okay? And suppose, okay, if we shift, we'll see how we can shift the zeros and poles and all later, right? Suppose due to some design process, right, I keep on shifting the 0, right, shift the 0 to minus 1, what's going to happen to P of S? We are going to have S plus 1 divided by S plus 1 times S plus 10. So what is it? Which one? So we'll look at it. Okay, so suppose if I say I shift the pole to minus 1, right? Sorry, 0 to minus 1, right? What's going to happen? The 0 is going to cancel the effect of the pole completely, okay? So what was a second order system to begin with would start acting like a first order system, okay? So this effect is what is called as a pole 0 cancellation. Okay, so but it is not a great tool. Okay, we'll see why we typically don't do this. Okay, so if you want to essentially cancel the effect of a pole, you can place a 0 exactly at the same location of that of the pole. So you can see that the pole and the 0 cancel off each other. Okay, but we'll shortly see, you know, when we start with the design process and analysis process, you know, like that this is something which we don't use typically. Okay, so no, it doesn't matter even if you want to do a pole 0 cancellation in the left off plane. Certainly when we want to we should not use this when we want to we are dealing with poles in the right of complex plane. Okay, we will certainly not do that. Okay, such pole 0 cancellations. Okay, we will see why. Right? Okay. So this is the effect of 0. Okay, like so we'll see that, you know, like I can introduce system zeros, you know, like when I'm doing control designs or design process. Okay, like we'll see that in fact, like if, for example, if you do what is called as a proportional derivative control. Okay, like so I can introduce a system 0, right, at that what to say, during that design process. Okay, then we need to be in a position as to how to handle those zeros. Okay, so that's something which we will learn, okay, as we go along. Okay, so but I hope we have got a picture, big picture viewpoint of what is the effect of zeros, right?